if I don't actually record there. Anyway, so we've already done, so just want to say, on Monday, we already did number 1, although I've changed it slightly. So you remember how at the end I was like, we should have number of steps rather than step size, just to make things cleaner. And so there's this slight, I'll show you the slight modification, so that instead of having the Euler's method with the H, you remember H, the step size, I've just got N, which is number of steps. That's just cleaner in terms of getting to where you're going. So we've got that. This is all pretty much, it's what we did. So this isn't a big deal. Taylor method order 2, we did pretty much, except for, once again, I've changed it to be step size instead of the, number of steps rather than step size. So I just made that change because I thought it's cleaner in terms of, like, that way you hit your target, because there's a chance you won't hit the target if you don't do it that way. So we did both of those. We did both of those last time. If I think I recorded, so if you need to, we can you can get that off the video, except for the fact that it's in here instead of H. So it's a minor change, not a big deal. Then the final one is the one that we didn't do last time, but I think you can handle this. I'm pretty sure you can handle the modification. It's just the Taylor method of order 3. So you remember Taylor method of order 1, all you need is the differential equation. Taylor method of order 2, you need the differential equation plus f prime, so you have to do the derivative. So that's not a big deal. Do your derivative's not that big of a deal. With Taylor method of order 3, you need the second derivative. So you have to take the differential equation, take the derivative of the differential equation, and we need this f prime prime second derivative. So I thought f prime prime was pretty descriptive. I don't know. But anyway, so that we didn't touch. But it's pretty much a cut and paste, and then you just modify just slightly. So if you can get Taylor 2 working, Taylor 3 is not a big deal. So anyway, we've got all those, and then, and so like I said, I haven't actually got, like when you look down here, there's nothing. Yeah, I don't have mine, but I'll have mine, don't worry, before Friday. I thought since this isn't due, or because I don't have mine to put here, I think I said it's due in, yeah, it's due 5 days, due Monday. So you got Monday, so plenty of time to deal with this. So hopefully I'll have mine up before Friday class time, so that you can look at it and see what it looks like, at least my output. Oh, sorry, final thing is test your code. Okay, so here's what I was thinking. So once again, I don't have mine yet, but I've pretty much done A. I just haven't got it in a nice form. But anyway, this differential equation with this initial condition, and this is the target. Oh, whoa. Oh, yeah. Yeah, no, this is correct. Sorry, I was misreading. Okay, differential equation, initial, I think we were using this differential equation last time, so as our example. So you should already have that sort of typed in. So this is the initial condition. Here's the different numbers of steps that you're going to test it with. And then I even put, this is the correct value. That is to say that the correct answer for y of 2 is 3.75. So just so that you know, like, you'll see that you'll get closer to this, I think. Wait, let me see. Now I'm worried. What have I done? Just a sec. Hold on a minute. Let me look at this real quick. What is going on? That doesn't make sense. Hold on a sec. I think that so-called correct value can't be correct. Hold on a minute. Okay, here, I'll pull up my, here, let's do this. This will help me. You can see that, can't you? Sorry, I can't see it either, so no problem. I'm going to zoom in. Okay, so I think, let me just make sure. Am I doing, oh, is this, oh, okay. So I think that I might have, go back here real quick. Where is it? This one. There it is. I think this is wrong. I need to update that. I don't know why did I think it was 3.75? I don't know what I was thinking. Because clearly it's not. If this is, yeah, if this is correct, oh no, this is a different differential equation, is it not? Hold on a minute. Sorry. So that's what we did last time. And this is in the instructions. Oh yeah, it's a different differential equation. Okay, so hopefully I got this right. So it's a different differential equation that I have there. So let's go back to what we did last time though, because I wanted to show you a couple things that I did. Okay, so this is last time. This is the differential equation we were solving. So just to remind you, those of you who haven't had differential equations, it's not that big of a deal. Differential equation is just an equation that has a solution that is a function. So like here, the solution is this, and you can double check that this is the solution to this by doing the derivative of this and then plugging that into here, and you'll find that if you take that, stick it in here for y, and then take the derivative of that, you'll actually get a balanced equation. And then of course, y of 1 is equal to 0.5 just means that when you plug 1 into here for x, let's double check. Sure enough, you get 0.5, you get 1/2. So that's what a differential equation is. It has this sort of overall, you're getting a solution that allows you to predict the future. That's the whole idea, is we want to predict the future using differential equations. This is what we use to predict the weather and also other things, like if we shoot, let's say we shoot a missile and hope that we're going to hit some target, we can use differential equations to sort of model the path of the missile based on assumptions about the atmosphere and so forth. Okay, so this is this. So what I wanted to show you is, so yeah, I was fooling around with mine. Yours won't look like this necessarily, but here I'll just point out that when you get done, yours would have looked almost exactly like this last time, except for instead of N, you have H. So there's an H there. Oh, and so what I did was I took, instead of H, I have N, and then I compute H is the first thing I do. That way, you remember the problem is that if, let's say that I want to go, I'm over here, and I want to get over there, and I want to go, say, 10 feet. Let's say I use a step size of 3. I'm not going to make it to 10 feet, because here's 3, here's 6, here's 9, and then if I take one more step, I'm going to overshoot the 10 feet. Now I'm at 12. So this way, it avoids that issue. So if you have N, then you can say, okay, my step size is going to be whatever, divide. Okay, so there's that. The other thing I wanted to show you is that, yeah, yours is going to look different than mine because I wanted to graph these things. I was curious to see what would happen if I graph them. So here, I'll show you the difference here. So here's the Taylor of order 1. Hold on a minute. Let's do 5 steps. Here we go. So I just wanted to show you this just to compare, because it's really stunning. I don't know, I find it stunning. So I changed mine so that I get both. This is the whole business with the X's and the Y's. I wanted both of them, access to them at least, so that I could use them for things like what I'm about to do. Wait, what is going on here? Did this actually run? Hold on a sec. Did it run? I think it ran. Let's try again. Yeah, it ran. Okay, give me a sec. Okay, so let's do this plot. My plots aren't, there's something weird going on, but I don't care. Okay, yeah, there. So check it out. This is, yeah, that's so terrible. Maybe I should plot both of them. So this is my Taylor 1, 5 steps. You can see I start up there. Yeah, you can't see the beginning. I'll zoom out. There it is. So you start up there, and it's like you take your first step. Now remember, Taylor 1, you're just going to follow the direction. And then you're here and you're like, okay, what direction should I go? I guess I'm going to go this direction. And then which direction do I go? I guess I'll go this way, and so on. And so this is really far. Look how far it is away from the truth when you get to the end of this. Now compare this with Taylor. You do this with Taylor 2. So the second order Taylor method is so much better. In fact, let's do this. Just rename those. Okay, so I've got my Taylor 2. And then I'm going to plot that. I'll plot all 3 of these. And yeah, I don't know what's, just a minute here. Give me a sec. Oh, I see. I don't need to print those. That's what's going on. Just a minute. Let me get rid of these print statements. We were doing a little bit of graphing last time, if you remember. And so let me just change this to a little O. I think that'll do it. Let's see. Oh, no. Oh, I see. Sorry. X2, Y2. Oh, there we go. That's so much better. Okay, so check it out. We've got, this is Taylor 1, it starts here. They all start here. So here are the points, pretty far away. Taylor 2, this is the second order Taylor method. It's almost spot on. Look how close it is. Super close. Taylor 3 is probably going to be even closer because you're using so much more information. Of course, it's more work too. But I just thought that that was kind of interesting that we could actually visually see. If you want to make plots like this, we started, I mean, it's not that much more work to make those plots. You can kind of see what I did here. You could watch the video and pause it if you want at the various places. But basically, I just, instead of outputting a single point, I outputted the entire vectors, X and Y, so that I could use those to make my plots. All right, so that's that. So this isn't due till Monday. So hopefully, like I said, by Friday, I'll have my because I have to rework this because now I've messed it up and it doesn't look like what I'm hoping you upload for me. Sorry. But I was just fooling around this morning and I was having fun. So I'll fix mine, get it ready for Friday, and then the stuff will be due Monday. So Friday we'll have a little bit of time if we need to fix anything. But before we switch gears here, was there anything that you're worried about or you're not sure how to do something? What do you think, Zane? Oh yeah. No, don't start a new one because yeah, that's the thing is I tried the instructions. So the instructions, well, I guess, whoa, what just happened? Okay. Let's see. I guess that, yeah, this is totally fine. I mean, yeah, just leave it. So the instructions say to have 3 blocks of code. I guess that if you use the stuff we used Monday, you have 4 blocks because you have this sort of starting code here where you have the importing and then you define some functions. That's convenient to have that. So that's totally fine. You can leave that. And then the main thing is you have one chunk where you have your Taylor 1, and then you'll have the like, why is it not showing me what I'm doing? It's blank. Okay, well, whatever. If it would show it to me, there's the Taylor 1, and then you would have the, wow, it almost looks like something got deleted. And then you'd have some, you'd be experimenting, so checking to make sure that that works. Then you'll do Taylor 2, make sure that works, and then Taylor 3. So once you get one of them that works, you can pretty much copy, like basically what I'm going to be doing here is, yeah, I've got this. Yeah, because we're not going to, here, I'll go back to the way I had it before. It was return yi. Is that what I think that was the final thing that we returned? And so I think that basically all you got to do is like do this, print. Yeah, so you'll have something like this where you do this, and then you'll have something similar. So print that for, you may want to have some labels of some sort. And then you'll have like F2, which I don't have defined yet, but it's in F2 prime or something like that. So you'll have the other function. So the other function is this, y minus 2 sine of x. And this is really easy. You can do the derivative of that really easily. Derivative of this is y prime minus 2 cosine. I hope we all know that derivative of sine is cosine. So that one's an easy one to deal with. Yeah, so I would suggest, yeah, stick with the code you have because it's pretty much, it works. And then you'll have to modify some here. So I'll have mine ready on Friday. But I mean, the main thing that you're going to do is, like, if I was working on this, you can ignore all this graphing nonsense down here. That's not going to be part of what you do. Let's see, what am I doing here? I need to add some code. Oh, sorry, wrong screen. Add code. Yeah, so I would probably like copy all of this and paste it in here and then make some modifications. So this will become Taylor 3, and then you'll need to have F prime prime right here. f prime prime, or whatever you want to call the second derivative, and then go down here and make some modifications. I think here is where you're going to put your new stuff, down here. Oh, and here we'll need a third derivative, second derivative, and then the third derivative. I know it's f prime prime. It's the second derivative of f, but it's the third derivative of y, because y, derivative of y is equal to f. There, let's go back to this picture. Where's the thing? There it is. Yeah. See, derivative of y is equal to, this is the function f. Derivative of y is f. And so second derivative of f is the third derivative of y. So, but you'll figure it out. If you can't, I'll help you on Friday. So Friday, I can help you. But yeah, start with the stuff you have. I wouldn't rewrite. Not worth it. Anything else? Other concerns? All right, so here's our goal for today, or at least to get started. I don't know if we're going to finish this. Is I want to know, can I predict? See how far off I am here? I'm really far away. I'm much closer with this. I want to know, can I predict? I think you know the answer, yes. Can I predict how far I am going to be, or at least give me an estimate of how far off I'm going to be so that I can know how many, like, if I shortened, obviously, I think you can guess that if I made the step size smaller, then I'm going to be closer to the truth. So if I can predict how close I am to the truth, then I'm going to be in good shape. I could pull up the PowerPoint, but I think that we can just do this using this here. Wait just a minute. Let's use the same differential equation. Give me a sec to write this down. So I'll use that one. That's the one we used last time. dy over dx is equal to xy squared minus y over x. Okay, good. And here we go. Okay, so this is just I want to get some error analysis, basically. So, and actually today, we're just going to compute the error involved in using the Taylor 1. Taylor 1, we'll deal with the others on Friday, but I just want to get the Taylor 1 down so that you can see. So this is going to be Taylor 1, error. Now here's the trick, is that since we're using a Taylor series, you already know about the error. Well, maybe you do, maybe you don't. Let's find out. So if we have a Taylor series or a Taylor polynomial, t, which we could go t1, is equal to the first order Taylor polynomial. I should probably capitalize Taylor because that's a name. So t1 of x usually, but this has an x and a y, so I'm just going to leave it as t1. And if you remember, we talked about r1 is the so-called remainder term. So it might be helpful just to remind you of this by actually making a first-order Taylor polynomial and getting a remainder for just a normal function. So let's take a simple function, a nice, easy function like arctangent of x. I know we all like arctangent of x. And what we'll do is we'll do the Taylor polynomial around x equals 0, because that's a nice, easy one. So let's do, so y equals arctangent of x. We need the derivative. So this is the warm-up. We'll do this as the warm-up. Is the Taylor polynomial for arctangent. It's a beautiful, it's a really amazing. The Taylor series expansion for arctangent is incredible, but that's really neither here nor there. We're going to just go ahead and get this polynomial. Okay, so let's see. I did attendance? Yes, I did. Excellent. So let's randomize. Let's do it. Oh, I didn't do attendance. There we go. Now I can randomize. Random it. All right, Matthew. What's the derivative of arctan? Do you remember? It's something, yes. No, tangent is secant squared. You didn't have me for calculus, so you can be forgiven. It's on a mug that I didn't bring with me today. It's my favorite, is arctangent, because it's a rational function. So we'll come back to you for the next one. Let's go around. I'll find someone else. I know you all know it. Eli knows it, right? You know what the derivative of arctangent is? It's been too long. It's been too long. Maybe Briar. Briar, you know it? Yes, whenever. Oh, I should have asked Grayson. She was in the play. It made a cameo appearance. That was amazing. It's such a happy moment to. But anyway. No, it's the integral, I think she said. Yeah, what's the integral of 1 over 1 plus x squared? And she's like, this isn't. Yeah. It's spectacular. But anyway, yeah, I think that was worth it right there. But the whole musical is incredible. But at least I thought it was great. Yeah, so derivative is 1 over 1 plus x squared. Very nice. And so let me remind myself or remind you what the first Taylor polynomial looks like. First Taylor polynomial, you're going to do t1 of x is equal to, first of all, we do the function value. I'll use y because this is a y here. Okay, so we'll do y evaluated at 0. And then we add to this y prime of 0 over 1 factorial times x minus 0. So that's the first Taylor polynomial. The second Taylor polynomial has an additional term. It would be y double prime of 0 over 2 factorial, but hopefully this is jogging your memory. But let's go ahead and do this one because it's so easy. So t1 of x, I need to know what the arctangent of 0 is. You know what that is probably, and if you don't, I'll help you. Don't worry. Rostin, do you know what the arctangent of 0 is? What angle? Yes, you got it. What angle has a tangent of 0? That's what arctangent means. It's like the Jeopardy, you're doing the opposite. So the angle that has a tangent of 0 is indeed 0. So that's kind of boring for our function, but still happy because it's easy. I probably should have picked pi over 4, but it's fine. Julia, do you know the what you get when you plug 0 into this thing, the derivative? Yeah, it's just 1. So that's a nice easy one. So that's going to be 1 times x minus 0. So this is just x. That's the first Taylor polynomial for arctan. Not very exciting. Okay, so now I need to know about the remainder. The remainder. So the remainder for a Taylor polynomial, I think we had this. Do you remember how horrible that first couple of weeks were when we were doing things like Taylor polynomials and figuring out how to compute absolute errors and all of that? Well, big O, big O, I know. But anyway, so does anyone remember? I won't pick anyone. I'm sure you all do. But what's the remainder term for a Taylor polynomial? You know it, Grayson? Yeah, it's the next term. That's basically it. So the remainder is the next term. So the remainder is going to be the next term. So I just mentioned what the next term would be. The next term is y double prime over 2 factorial times x minus 0. Now, hold on a minute. It's this y double prime. This is where things get a little funky. And that is that because of the mean value theorem, the mean value theorem says that there is somewhere in between 0 and x where this is going to be an exact number. Well, it's a little bit more complicated than that, but it relies on the mean value theorem. At any rate, and so because we don't know what the number is, so here, I'll remind you what the mean value theorem says. This is that if you have a function and you pick 2 points on that function, so this is the mean value theorem, the slope of that line, there is a point, as long as you've got a continuous function, there is somewhere in between A and B that has a slope equal to the slope of this line. So somewhere right there. That's where it's, so right there is the answer. Yeah. So that's the mean value theorem, and slope is derivative. And so it's basically the same idea, except for we're dealing with the second derivative. So this ends up being c, this weird Greek letter. So we've got y double prime somewhere between x and 0. So what is this? This number is somewhere between x and 0. Okay, so I guess I need to know what y double prime is. Oh no. Okay, before I do y double prime, let us fix y prime so it's a little easier. So 1 plus x squared to the negative first power. Okay, now we can do y double prime. I just didn't want to use the quotient rule if I could avoid it. You know how it is. Quotient is painful. Zane, now that I've got this written like this, can you apply the chain rule or the power rule to do the derivative of that thing? Wait, oh, 2x. Yeah. Okay, sorry. Yeah, I was thinking of it in a different order than you. It's good. Yeah, good. Okay, 2x. Go ahead. Beautiful. Yeah, so using the chain rule, you know that you do the derivative, you take that negative and put it out front, change the negative to -2, and then multiply by the derivative of that stuff. Well done. Okay, so that's my second derivative. So when I go down here, I just want to know what's the worst case scenario is what I'll do is I'll say, okay, I don't know what the value of xi is, but I can say that this remainder will be less than or equal to the maximum of y double prime over 2 factorial times whatever. So we would need to have, like, let's do x equals pi over 4 just for, arctangent, sorry, arctangent. Let's do x equals 1 just for fun. Okay, so x equals 1. What that means is I'm going to evaluate this using this Taylor polynomial at x equals 1. So arctan of 1 is approximately equal to 1. How far off might I be when I do this using that polynomial? Well, between 0 and 1, there is a xi that will make this perfect, but I don't know what it is, and so I'm going to just use the maximum. So looking at this, let me see if we can just ascertain the very worst, the biggest this would ever be between 0 and 1. Wow, this is not going to be as easy as I thought. Maybe I should graph this. Let's do it. I know this is cheater time now. Give me a sec here. Just a sec. Where is my? Here we go. Reconnect. I was going to use. Yeah, you'll see. I've got a Python sheet here that I use for calculus. It's actually called calculus, so that I can avoid having to do too much work. Certain types of work. Okay, so let's see, plot. I'll show you what I've got. It'll be easier if I type it like this. What is this? 2x over 1. Here, just a minute, I'll show you what it's that. And I'm going to make this positive because all I care about is the magnitude, how big this is. So I'm going to plot 2 times x over 1 plus 2 x squared. Let me see, just checking my syntax. X from 0 to 1. Okay, I'll show you what I've got. I hope it works. Yes, it did. Here, I'll bring it over. You can see. Yeah, like I said, I've got this sheet. I've got all kinds of like calculate. Oh, there's only a couple of things. I've got another one that has more. But you can see, look at that. It maxes out. So I didn't want, I was too lazy to work this out. But it looks like it maxes out a little over 0.6. So we could say that for sure it's less than 0.75. This is the second derivative. Second derivative is never bigger than it looks like it's never bigger than 0.65, but maybe 0.7 we should use. So in other words, this thing is going to be less than 0.7. To do it right in calculus class, you would actually want to find where that is a maximum using optimization, but I don't want to do it. So let's just do it the quick way. So what does this mean? This means that my remainder is less than or equal to 0.7 over 2 times 1 minus 0. This is not all that great. So I'm up to 0.35 away from the truth. I guess I can go back to Python and actually find out how close I am to the truth. Now, let's see, I'll just do it right here. So give me a sec. Arctan of 1. Oh, actually, I know the arctan of 1. We should all know the arctan. What angle has a tangent of 1? Anyone know? You know it? Oh, yeah. It's pi over 4. Pi over 4 has a tangent of 1. So pi over 4, which is what is pi over 4? 0.78? something like that, in the around 0.78, I think. So that means that, oh, this was a pretty good prediction. See, my polynomial gave me this, and my remainder was this. So yeah, I am within 0.35 of the truth, for sure. Okay, so that's a quick reminder of that. Now let's go back to the problem at hand. The problem at hand is using Taylor 1 method and finding the error. I know I just went through all that rigmarole, but now we got to go back. Okay, so let's remind ourselves, what does this mean? We have the remainder. So you know the Taylor 1 method. Now here's the key, is that the remainder is equal to the second derivative, which is going to be, if this thing, here we go, that thing is f, then the second derivative of y is the first derivative of f. So just want to point that out. Evaluated at some c. I've got a little blank space there, I'll explain in a minute. Over 2 factorial. And this is going to be, oh, here's what we're going to do with this. Instead of saying x minus 0 or whatever, this is just the step size. That's all that is down there. That x minus 0, it's how far have I stepped? How far have I gone? I'm here at 0. I'm going to go to 1. Okay, I've gone to 1. And now, what's my new value? Okay, so back here, doing this differential equation, because this is a differential equation, we don't have just a function of one variable, we have a function of 2 variables. And so I think our book uses mu. Just basically, it's just saying that there is some point between. So here's the way that this is going to look. Let me get the picture. Give me a sec here. Where's my picture? Hold on a sec. I had it. You remember that? Just a minute. That's not the picture. Why is this so hard to find? Oh, here it is. There we go. That's what I wanted. Okay. So there is some point between the start, yeah, it's up here, and here, some point in this sort of like grid, if you will, or in this rectangle, some point that is going to give you an exact value for the remainder. And so that's what that is. So instead of just dealing with one dimension, we have to deal with 2 dimensions, but that's our remainder term. It's pretty much the same thing. It's a similar idea, similar calculation. So let's see if we can figure this one out. So for this one, how far off could I be? So remember, we're starting at the point, what was our initial value here? Sorry, I got to remember 1 and 0.5. Really? Is that what I started at? Oh, yeah, y of 1 is 0.5. Okay, y of 1 is 0.5. Okay, so we have, here, I need to move this down because I have all these extra notes. Give me a second. Copy. Here. Paste. Okay, so this is f. Okay, so we have y of 1 is 0.5. And then I guess I need to get that first step so that I can more intelligently do this. But so my h was 0.2. That was the step size. And then, so here's this. And then I think that's, yeah, I guess we could do y of 1.2. Well, let's leave that off for now. Okay, so let's see if we can get a good estimate of this. So let's take this and do the derivative. I know we did this before, but it would be good for you to do it again. See if you can get a derivative of this. Remember, you're using the product rule here, quotient rule there. I know it's kind of painful, but oh, actually, didn't we avoid the quotient rule? Use the product rule there as well. So let's get our derivative. Well, actually, you've got it in your notes, don't you? Just a minute. It's right here. Here. There it is. So you've already done this, so it's right there. So let me just copy that back here. So what we got here is y squared plus 2xy times y prime, and y prime is this. And then we're going to subtract off y prime over x. So give me a sec here. Xy squared minus y over x. And then I'm using the product rule here. So this is going to be minus a negative y over x squared. I think that's what we had. Wow, that is super complicated. I'm really disappointed in how complicated this is. Okay, so the tricky thing is, I want to know how big could this be? What's the worst case scenario? Worst case scenario. Okay, I'm going to be lazy with this, if you don't mind. And here's how I'm going to do the worst case scenario is I'm going to just pick numbers that are pretty big. So in this range, so that looks like the biggest that y is 0.5. Biggest that y is 0.5. And the reason why I'm picking that is because if you notice here, all of my y's are in the numerator. So in all likelihood, that's going to, if I pick the biggest y that I can get, that's probably going to give me our biggest error. So, or the biggest value for f prime. And then x, yeah, I don't even know what to do with the x because you have x squared over here. But if I pick a large value for x instead of a small value, since x is bigger than 1 to begin with, I know that's going to become smaller when you pick bigger values of x, but this will be big as well. So let's do y equals 0.5 and x equals, say, 1 or even 2. Yeah, because you'll notice that eventually I'm going to get over to 2 with this picture. This is x equals 2 over here. So we just want to get an estimate for our error. So let's just go with, this is going to be super coarse, not very good error estimate. We want to do some calculus to get a better error estimate, but let's use something like, how about this? That we think that f will be less than, let's use 0.5 for y, 2 times, let's use 2 for x, just to say that that's the worst it could ever be, at least on the interval that we're working on, 0.5, and then this will be 2 times 0.5 squared minus, let's not even compute that part, because I want to get like the worst case scenario. And then here, this stuff, well here, this stuff we're subtracting, so I'm not going to bother subtracting off anything. I'll just keep it as big as possible. And then this is just a small thing, but I guess I could put it in. So plus 0.5 over 2 squared. So basically, this is a really, really bad estimate. I just want to get an estimate for how bad things could be. It's not a very good estimate, but let's go ahead and do it anyway. So 2.5 plus, let's see, this is going to be 4. This is that's going to be 2 times 2 times this is going to be 0.5. Yeah, this is a terrible estimate. And this is 0.125. So let's add all this up. I get 1.375. So this, for sure, I'm pretty sure that we could say that this function will never be bigger than this in the interval that we're talking about here. So I know that this is really not that great of an estimate, but I just wanted to get something on paper. So now let's plug that into here to get an estimate for the remainder. So the remainder will be less than that over 2, 2 factorial is 2, times the step size. Now here's the key. So 0.2 is my step size. So let's see what that ends up being. This I'm going to need a calculator for. But I have one over here. Because I can't do that. And, well, I probably could do it in my head. But 1.375 divided by 2 times 0.2. Surely that's not right. Just a minute. Let me try again. 1.375 divided by 2 times 0.2. Okay, that's better. So I'm getting, oh, that makes sense. I don't know why I had to do this on my calculator. Okay, so that tells me that the worst case scenario is that my error is going to be about 0.1375. So you can see that it's actually less than that. It's actually considerably less, probably because I did such a poor job in computing that error. But nonetheless, 0.1375, actually it's more like, what is this, about 0.05, isn't it? From here to here, about 0.0, oh, I'm sorry. It's actually this, it's much better. That's more like 0.01. So I'm off by a factor of 10. But suffice it to say, you'll notice that this is now about double, and then this is about triple, and this is about quadruple. So each time I take a step, I'm going to add to my total error as I go around this curve. And so once I have an estimate for the error, I just multiply by the number of steps, and that gets me sort of the total error for the whole procedure here. Now the problem here is that this is all based on your step size. So this step size controls how bad things are going to be. So if I change the step size, if I make the step size smaller, I should have smaller error, and so on. But this is not a very good, it's not a very good method, because if I make the step size smaller, it doesn't really change the error by that much. I guess that's what I'm trying to say, especially when you factor in that I'm going to end up multiplying the whole thing, because I'm going to be taking however many steps. I'm going to be multiplying by n. And so these two things end up canceling each other out, because you have number of steps, step size, you pretty much, you're always going to get the same number when you do that, no matter what your step size is. Take one giant step, or you take 1,000,000 steps, and when you multiply those two together, you're going to get the same number. So anyway, that just shows you that this isn't the greatest method. Now, what it turns out is that when you do the Taylor 2 method, the error, which I'm not going to subject you to because it's much more complicated, but it's in your book. So the R2, I guess it's of xy now, is going to be on the order of h squared. So this is on the order of h. Get rid of that, because you've got that h there. This is on the order of h squared. That's much better, because, as you'll see, the step size, you're taking the step size, here the step size is 0.2, and you square it, and so as long as your step size is less than 1, that's going to make your error really small. So that h squared is going to really benefit you. And then, of course, the order 3, you're going to have a h cubed when we do this. All right, well, we got about 10 minutes. So I guess we do have time if you want to pull up your thing and work on it. But if you don't want to, that's fine. I understand. So this is this thing. So if you're like, oh, I don't know if I can do Taylor 3, you can get started on it now and get it going. In fact, maybe I'll type mine in right now so you can follow along if you want to. Otherwise, you don't have to. But I'll have mine done by Friday and have my PDF uploaded. I'll also have some paper homework, not for today, but eventually we'll have paper homework where you're computing some errors. Don't worry, we'll go over some more examples on Friday so that you know what to do. So that's it. I'm going to stop the recording.